Hello and welcome to this lecture number 6 of the course Introduction to Robotics. In the last class we looked at DH parameters, that is how to assign axis and frames to every axis on the link, and today we'll see further about the general transformation matrix which is very useful for getting the transformation from any frame to some other frame. Okay, so today we look at derivation of link transformations. And I will go very slowly at the moment because how to assign axis using DH notation is very important in robotics, and it should be very clear that how are axes assigned, and based on which how we make the DH parameter table, and then how do we find the link transformations. So let's proceed. I'll very quickly revise the section on how to assign frames. We have seen in the last class that if we take a link of any shape, for example, this is a link in 3 dimensions, so it can have any kind of a shape. Okay, and so this is a link. Okay, and it is connected to another link on the other side. So this is one link, and there is another link on this side, and this is connected to a linkage here. Okay, so this is how it works. So this is one link. We can call this link I-1. The next link is I. Okay, and this is an axis. Now we have seen in the last class that if you have a single link, then for the single link there are 2 parameters which define the relation between the 2 axes, and they are alpha, the twist angle, and the link length A. Today we'll see that if you want to go from one link to another link, then what more parameters are required. So the first thing that we have seen in the last class is we need to assign axis. So this is my axis, this is the revolute joint. So in the revolute joint we assign axis like this. Okay, and then the z-axis is the axis of translation here. So this is my z-axis, axis is here, axis is there. Now let us say that I'm taking my z-axis in this direction here. Okay, this is my z, and this is my zi-1. Okay, and in this particular case the zi-1 is here. Sorry, zi is there. So the I-1 to I. Now in the last class we saw that there are 2 parameters which define the relation between the axis of one link. Now those 2 parameters are the link angle alpha. So we can notice that the z-axis has an angle between them, right? So what I do is I draw a parallel line like this. So this is parallel to this. Okay, and I rotate my angle zi-1 by an angle alpha. So the first parameter is alpha. Then what happens is if I rotate it like this, now you can see that zi-1 has come here. Now zi-1 and zi are parallel now. So what I can do next is I can move it along the shortest distance like this. Okay, this is the shortest distance, and this is my distance A. And now I put my xi axis along this direction. This is my xi-1 axis. So y axis I'm not writing because as per right hand rule, if you have z and x, y is automatically fixed. Now the next parameter that the next transform that we do is I move the origin of frame zi-1 by a distance A, and it comes here. Okay, so now my zi-1 is here. Okay, this is my zi-1, this is my xi, x of I-1, and on the top we have zi, and maybe this is my xi. Okay, now we see that we have the second transform, which is A. Now we see that there is an angle between xi-1 and xi. So what I do next is I rotate by an angle. So I rotate this by an angle theta. So my xi-1 comes here, and this becomes parallel to that. So that's my angle theta. So that's my angle theta now. Okay, the next transform is theta. Now there is a distance between the origins, so I move the origins up by a distance d, and this is my distance d now. So what we have done, first what we did is I rotated the angle, I rotated the zi-1 axis by an angle alpha and made it parallel to zi. So that's my first transform. The second transformation is I moved the origin by a distance a to here. So that's my second. Okay. Then I rotated the xi-1 and made it parallel to xi. And this is my third transformation. And the fourth transform is I moved the origins up by a distance d, and this becomes my fourth transformation. So essentially we have 4 transformations, alpha, a, theta, and d. And one is, this is called the twist angle. Okay, this is the link length. This is my angle, the link angle, and this is my offset distance. This is something we saw in the last class. Now you should be very, very clear about how do we assign our z-axis. Z-axis is the axis of rotation and translation. X-axis is the shortest distance between the z's, and if they are perpendicular, if they are intersecting, then it's perpendicular to the plane containing the z's. Now, if I write 4 transformations, one for alpha, one for A, one for theta, and one for D, then what will happen is I can multiply them out and I'll get one matrix which is going to relate all the transformations. Okay, what is going to relate xi to xi minus 1 in terms of frames. Okay, so what I'm saying here is that the total transform, I can write it as there is a rotation. Okay, so the total transformation I can write is the rotation of alpha. So there is a rotation of alpha. Then there is a distance which is moving. Okay, that is my A. Then there is a rotation about theta, and then there is a distance which is moving about t. So this is translation, translation, rotation, rotation. And if I multiply them out, put the corresponding values and multiply it out, we get the generalized matrix which is given by cos theta I, cos theta minus sin theta, okay, 0, ai minus 1. So there is a convention of writing ai minus 1 and I. Here it is sin theta I, alpha minus I, cos theta into cos alpha minus I. This is minus sin alpha minus I, sorry, I minus alpha. This is equal to minus sin alpha I minus 1 and di. Okay, and this one is sin theta I, sin alpha I minus 1. This is cos theta I and sin alpha minus I minus 1, cos alpha I minus 1 and cos alpha I minus 1 di, 0, 0, 0, 1. Now, how this is useful is that we can directly find the transformation matrix from one frame to another frame which has undergone rotations and transformations. Okay, I'll explain how. And in a robot kinematic analysis, we are rarely going to do this by hand. Okay, because if you have 6 links, you can see how many transformation matrices are going to come. So it will become very cumbersome, and there's a high chance of a mistake. So what we do is we write a computer program which will actually do this. So systematically, what is done is we assign our let me write this down. So we assign our the axis as per DH notations. Then I put each row of the DH parameter table, okay, in this matrix, and I find the corresponding matrices, which will take me from one frame to the other frame. Okay, so as I go along, I'll be explaining how that is done. Now, for simplicity, I can also write this as I can erase this I minus 1 and I subscripts. Okay, so this is AI, this is A, and I will simply take the corresponding values from the DH parameter table and put it in here. Okay, so that is how we are going to do our. That is how we are going to find our transformation matrix from one frame to the other frame. Okay, this is for simplicity. I am just removing the I and the I minus 1. You understand what they mean. So basically, we'll be taking each row from the DH parameter table, looking at the values of theta, alpha, and d, and putting it in here. Now, is this DH parameter method unique, the way of assigning axis? No, it's not unique. So if you look at, let's look at this example where we have a manipulator like this. Okay, this is a revolute joint, and we have another revolute joint here. So this is another revolute joint, and we have another one here. So this is the way it is moved, one joint to another joint. Okay. Now, if this is one joint, this is another joint. Okay. So let me draw with some other color. So let me draw the axis. So this is one axis. This is another axis. Okay. So one way of assigning the frames would be I can assign Z1 here. Okay. And I can assign X1 here. And this is my Y1. Okay. On the other, I'm going to put Z2 here. Okay. Then I put Y2 here. And I'm going to put X2 here. Okay. Now, this is one way. What is the other way? The other way could be that I put Z1, X1, and Y1 like this. But what I do, I can reverse the Z2 and put it this side. This is my Z2 now. okay, and my x2 is this side only. Okay, why? Because this axis here goes in this direction and also this direction to infinity. So it could be pointing this side or it could be pointing this side. It's the same thing. Okay, so this basically shows that the assignment of DH parameter is not unique, but the answer will be the same. Okay, why? Because well, we'll come to it why the answer will be the same. But this is very important to understand that there are different ways of assigning the DH notation. Why? Because an axis can be positive up or it can be positive down depending on which side you're seeing it from. Okay, so now let's move on now and try and assign an axis using DH notation just for practice before I move on to the new topic. Now let us look at this manipulator system here. It has one axis here, that is my prismatic axis. Okay, so there is a prismatic distance which is d1. Next is there is a rotation axis here, so that is my revolute joint. Then there is a rotation axis here which is the revolute joint again. Now how do we assign DH parameters to this manipulator? Based on what we studied in the last class, z-axis is axis of rotation. Okay, so this is the axis of rotation or translation. So the first axis that we assign is here. Okay, so I say this is my z0 and z1. Okay, now next axis is this axis which is my z2. Then there is one axis there which is my z3. Right, now I have assigned my z-axis. Now I want to assign my x-axis. So x-axis, they are all parallel axes, right? So what we can do is I can assign my x-axis this side. Okay, so this is my x0 and x1. I can assign x2 here. They should look parallel. So this is okay, so it is so x2 is here and x3 is here. Okay, so if you can visualize, so when this joint 1 moves, what will happen is the 0 frame will remain here only. Okay, that means the 0 frame is fixed onto this link. Okay, that is my 0 frame. The first frame is going to move up and down. So what will happen? The distance between x0 and x1 is going to change. Okay, and when this rotates, when joint 2 and joint 3 rotates, what will happen? The angle between x1 and x2 is going to change. Okay, if you can visualize, if I take the top view, so this is my x1 and x2. Okay, so when x2 rotates, x2 goes there, this angle will change. Okay, so x1 will still remain there only. So what you can see is that based on this, we have assigned our frames. Now you can write your DH parameter table. Okay, now let's look at another example of the derivation of link transformations. That is, when you want to go from one link to the other link. We have found out the combined transformation matrix. Now let us look at an example of how to use that matrix and get the transformation matrix from one link to the other link. So let me write it here. This is just to take this example. We had done it in the last class, but let's do it again. Okay, just for practice. This is very simple, but it's very important. You should know this definitely. So I assign my z0, z1, z2, z3. Okay, and this is my x0. This is my x1, x2, x2 and x3. This is the link lengths L1, L2, and this is L3. Okay, what is the generalized matrix? The generalized matrix T, which takes you from one frame to another frame, is equal to cos theta minus sin theta 0 AI. Let's call it A only. I'm just leaving the subscript of sin theta cos alpha, cos theta cos alpha, sin alpha D. This is sin theta sin alpha, cos theta cos alpha. Sorry, cos theta sin alpha. Cos theta sin alpha. This is cos alpha D, and this is 0, 0, 0, 1. Okay. Now this is the generalized matrix that is going to take you from I to I minus 1. Sorry, I minus 1 to I. Okay. So from one frame to another frame. Now let's make the DH parameter table for this manipulator. I had done it, I think, in the last class. So the DH parameter table for this manipulator is equal to A alpha D theta, and this is 1, 2, 3 joints. Okay, so the first joint is 0, 0, 0. Please look at the previous lecture where I derived this and explained very clearly how we find this. This is theta 1, This is L1, this is 0, 0, theta 2, and it is L2, 0, 0, theta 3. Okay. Now, the meaning of A alpha d theta, A is the distance between the z-axis, alpha is the angle between z-axis, d is the distance between x-axis, and theta is the angle, sorry, d is the distance between x-axis, and theta is the angle between x-axis. Now, what we want to do is we want to find each of the transformation matrices T 0 to 1. Okay. What is this matrix? Okay. Then I need to find T 1 to 2. Okay. What is this matrix? Okay. Then the third matrix T 2 to 3. What is this matrix? Okay. I want to find each of these matrices. So T 0 to 1 relates the first matrix to the base frame 0. Okay. Now, why do I need to get this? Because I want to go from 0 frame to third frame. Okay. So if I need to go from 0 frame to the third frame, then what I'm going to get is T0 to 1, T1 to 2, and T2 to 3. I just multiply them out. So what we get here is 0, 0, 0, 1. Now, we take each row of this DH parameter table. This is my DH parameter table, and this is the row number 1. What is the value? 0, 0, 0, theta 1. So this is the row that I'm catching first. Now this row I'm going to put in this generalized matrix. So take the value of theta. The only variable is theta 1. So I say cos theta 1 minus sin theta 1. A is 0, right? So cos theta 1 and minus sin theta 1, sin 1 I'm writing, 0. A is equal to 0, so it is 0. Now sin theta, cos alpha. How much is alpha? Alpha is 0, so it's 1. So sin 1 cos 1. Okay. Now sin alpha is equal to 0 again, and that is equal to 0. What about the third one? The third is sin theta, sin alpha. Alpha is equal to 0. So this becomes 0. So it becomes 0, 0. And cos alpha is 1. So it becomes 1, and this becomes 0. So that is our first matrix. Now I take the second row from here and I put it in this matrix. That is going to give me 1 to 2. So 1 to 2 is this matrix here. Okay, so this is my matrix T 1 to 2. Okay. So what is the values? A is L1, alpha is 0, D is 0, and theta is theta 2. Okay, that's the variable. Now I take these values and put it into this generalized matrix. So it becomes cos theta, cos 2 minus sin 2, 0. And the second term, cos alpha is 1. So sin theta becomes sin 2. Then again cos alpha is 0. Cos alpha is 1. So it becomes sin theta. Sin theta, cos theta, and sin alpha is equal to 0. Okay. Now sin theta, sin alpha, that is equal to 0. Okay. And again cos theta, sin alpha, again equal to 0. And then we have cos alpha, which is equal to 1. Now the last term is always 0, 0, 0, 1. Okay. So that's my rotation matrix. Next I have, what do we have? We have a A. What is A equal to? A is equal to L1. Okay. So this is my L1. What is sin alpha? Is 0. And cos alpha into D, D is 0, so this is 0. So that's my second matrix. This relates the frame 2 to the frame 1. Then I take the third row and I put it in that matrix. Okay, so you can see what is A is equal to L2, then is 0, 0, theta 3. So the variable is theta 3, and A is equal to L2. So again we get cos 3 minus sin 3, and then what we're going to get is sin 3 cos 3, 0, 0, 1. 0, 0, and this is going to be 0, 0, 0, and that is going to be equal to 1, right? Now what is A? A is equal to L2. L2 sin alpha is equal to 0, and D is equal to 0, so this is 0, and that's 0. Okay. So what we did is we took each of these rows of the DH parameter table and we put it into this generalized matrix, and we got our corresponding rotation matrices. Then next what I'm going to do is I'm going to multiply all of this, and we'll get the final, the third frame with reference to the 0 frame. Okay. So this is how we proceed in doing the next. What we'll be doing is forward kinematics and then inverse kinematics. But this is how we derive each of the rotation matrices, by using this generalized matrix. So we're going to write a computer program which is actually going to make the DH parameter table, or you're going to enter the DH parameter table. The computer program will take this array. So the DH table is a matrix, and every time it takes one array from that matrix or one row, puts it in the generalized matrix, and gets the transformation matrix between the two corresponding frames. Okay, and this is generalized, so it can take any frame to any other frame. And we have seen that when you want to go from any frame to any other frame, basically what we are getting is we are getting 4 variables. Okay, and this is the generalized matrix. Okay, so this matrix is very, very important to understand that why there are 4 variables and what is the generalized matrix and how do you proceed. Now let's look at this is a very, very simple example that we just solved. Let's look at another example before we go on. So the other example we are looking at is we had looked at an example which was given here. So this is the manipulator. Okay, so this is the manipulator. First we need to understand how it moves. Okay, first thing we are trying to do is to understand how it moves. Okay. Now what are the axes? This is my θ1. Okay, then this is my θ2. So this axis is my θ2 axis, and that's my θ3 axis. θ1, θ2, and θ3. So it's 3 revolute joints, 3 arc joints. Okay. Now let's assign the axis, and then we will proceed. So let us assign the axis. The first axis is here. Okay, Z0, Z1, Z2 is here, and Z3 is here. That's my Z3 axis. Then X. Now we see that Z1, Z2 are intersecting. So we have to be careful about this, that for intersecting axis, the X-axis points out of the plane. So it's X0, X1, and X2. This one is X3. Okay. So we have put our axis. Now let's write the DH parameter table, our DH table. So our DH parameter table will be A alpha, D, and theta. And our table will look something like this. So the first one we start off by is 0, 0, 0, θ1. Okay, that's my first DH parameter table. What is the second? Second is, so this is 1, 2, 3. This is 0 to 1. This is 1 to 2. And this is 2 to 3. Right? For the first frame, they both have the same origin, and the variable is θ1. For the second one, they are rotated. So there is no distance between the origins, or there is no distance between z axis because they are intersecting at the origin. Alpha is minus 90, so there is a rotation clockwise like this about the x-axis, so there is a minus 90 there. Distance is not there because the origins are intersecting. Theta is equal to θ2. Okay, then for the third one, where is the third axis? Now for the third axis, you see that this x is here on this plane, if you can imagine. Okay, so it is on this plane. So there is a distance here, there is a distance here, and plus there is a distance here. So there is a link length here, and plus there is an offset distance there. So what is A? A is the distance between Z. What is that? Let us say it is L2. Okay, L2 is the distance between the Z axis, Z2 and Z3 is my L2. Okay. What is alpha? The Z2 and Z3 are parallel, so this is 0. What is D? D is the distance between X axis. So let's call this A2. Okay, so this is my A2, and the variable is θ3. Okay, so this is my DH parameter table for this matrix, for this manipulator. So now what we are seeing is that I need to find the generalized matrices, which will take me from one frame to another frame. So what I do is I start off by taking this row, putting it in the generalized matrix. So in this generalized matrix, so I take that first row, put it in this matrix, get the first one. Then I take the second row, put it in that matrix. Then I take this one and put it in that matrix. Okay. So with that, I'm going to get T0 to 1, which is equal to cos θ1 minus sin θ1, sin θ1 cos θ1, 0, 0, 1, 0, 0. And then this is 0, 0, 0, 1, 0, 0, 0. This is the first one. Okay. The second one I'm going to get is T1 to 2, which is given by, take the second one. Just note that there is an alpha there. There is an alpha of minus 90 there. So what we are going to get is cos 2 minus sin 2, 0, 0. Or let me write it shorter. There will be no space. C2 sin 2, 0, 0. And this is 0, 0, 1, 0. This is minus θ2 minus cos 2, 0 0 and this is 0 0 0 1. Okay, so this is the second one. You should note that there is an alpha there, and that alpha causes this matrix to appear. Now for the third one, what we do is T2 to 3. I take the third row, that is this row. This one has a distance L2 and A2. Okay, so what we do is we get cos 3 minus sine 3, sine 3 cos 3, sine 3 cos 3, 0 0 1 0 0. This is 0 0 0 1. Now what is the distance? What is A2? A2 is the distance of the link length, so we get L2 here, and there is an offset distance which is equal to A2. Okay, that is my D distance between the x-axis. So we have got T1 to 0, then we have got T2 to 1, then we have got T3 to 2. Now I can multiply all these three and I can end up with T third frame to the 0th frame. Okay, so this is the way we proceed. Now a computer program would do it. When you write a program, it is going to be executed like this, where we have to make this DH parameter table, which is a matrix. So at every time it will take one array, one row, put it in the generalized matrix and get the corresponding matrix. Okay, so what we have to enter this into the computer, the generalized matrix. This matrix will be entered, and every time it is going to put the values of theta, alpha, D and A, get the corresponding matrix. Okay, then multiply them all out and get your final transformation matrix between the end effector and the base frame. Now let's proceed a little bit more to look at industrial manipulators. Let's look at before industrial manipulators, let's look at SCARA robot. We talked about SCARA robot. So the SCARA is the selective compliance assembly robot arm. This is an industrial manipulator which is used for electronic assembly. So this is used for electronic assembly. Okay, so basically this is my okay. So now we have this 4 degree of freedom system. Now what we'll do is we'll assign the DH parameter table. So first we're going to assign the axis as per DH notation. Then we're going to assign DH parameter table, make the table, then take each row of the table and make the corresponding frame to frame transformations. So first let's look at how does this move. Okay, so where is my first axis? This is my first axis, it's a rotation axis. Okay, this is my second axis, which is also a rotation axis. The third axis is a prismatic axis, which is translating, and the fourth axis is a rotation axis. So I put my, just to simplify, this is my Z0, Z1, this is Z2, this is this one is Z3. Okay, please note that Z3 is fitted onto this link. Okay, and this is my Z4. Also note that Z4 is pointing downward, Z3 is upward and Z4 is downward. My x-axis, my x0, x1, this is x2, this is my x3, and this is my x4. Okay, so we have put our frames as per DH notation. Now this is the link length, distance between the z-axis. This is L2, this one is D3, which is the variable, and there is a distance from here to here. There is a distance, let's say it is L4. Okay, so now we have to write our DH parameter table. So our DH table is given by A alpha D theta, and as I explained in my last class, when you are doing this, you should actually write on top. So A is the distance between Z, this is the angle between Z, this is the distance between X, and this is the angle between X. Okay, if you write it like that, you won't forget. Now there are 4 degrees of freedom, 1, 2, 3, and 4. These are my 4 degrees of freedom. Okay, so now what we're trying to do is we are trying to write our DH parameter table. So let's start off by looking at the first axis. So 0 and 1 frame. What is the variable? So when the first joint rotates, what changes is the angle theta 1. Okay, there is no distance between the Z, there is no angle between the Z, there is no distance between X, and the variable is theta 1. So the next is the relation between the second frame and the first frame. So if you look at the second frame, there is a distance of L1 between the Z-axis. There is no angle between them, they are parallel. there is no distance between x-axis. Okay, so it is 0 and this is theta 2. Now in case just note that I've taken my origins here and here, so z1, x1 and x2 are aligned. If I take my x2 here, okay, then this distance is there. Okay, then a particular distance will come there. Actually the link has a thickness, so some distance should be there, but just for simplicity what we are doing is we are saying that that is not there. Okay, just note this. Now this is the second one. The third is a prismatic joint. Okay, so theta is equal to 0, it doesn't move, and there is no theta there. So what is the distance between the, this is L2, what is the distance between the z-axis? It is L2. What is the angle between z-axis? It is 0. What is the distance between x-axis? Now when this goes up and down, what will happen is the third axis, the origin of the third axis will start going up or down. So there will be a distance between the z-axis now, z3 and z2, that distance will come. So what we are getting is a variable here, d3. Okay, so when this goes up and down, what happens, the origin of the third frame is sitting on this link, so it is going to go up or down with this link, which means there is going to be a distance between the x2 and x3. That is my d3, which is the variable. What about the fourth one? The distance between z, there is no distance between z because it's the same axis. Angle between z, now z3 is upward and z4 is downward, so it is 180 degrees. Now it can be either clockwise or it can be anti-clockwise. It's the same thing, because you can rotate clockwise or anti-clockwise, and z3 can become z4 in both ways. If I see from the front, this is my z3, this is my z4, so I can rotate like this by 180, or I can rotate like this by 180. Okay, this is plus and that is minus. In both cases it will become the same. Okay, but it doesn't make any difference. It is 180 plus or minus, it won't make any difference. So here I'm writing 180 plus. What is d? D is my distance between x-axis, which is L4, and the variable is theta 3. Okay, so I have written my DH parameter table for the scalar manipulator. Now what we need to do is I need to write the matrices. Okay, so the first matrix is T 0 to 1. This is very easy because you can see that the Z, the 0 axis and the first axis frames are the same. So here I'm going to write cos 2 or cos 1 minus sin 1, 0 0 1, sin 1 cos 1 0 0. This is 0 0 0. That's 0 0 0 1. What we are doing, or what the program would do, is it will take this one, the first one, put it in the generalized matrix and get this. Then it will take this one, put it in the generalized matrix, and what it will get is T1 to 2, which is equal to cos 2 minus sin 2 cos 2, 0 0 1 0 0. This is L1 0 0, that is 0 0 0 1. Okay, this is what we have got, the second one. Now let's look at the third one. The third fellow is having an L2, it is having a D3 also. Okay, and the D3 is the variable. So what will T2 to 3 be equal to? So we take this third row, put in the generalized matrix. Now what you see here, there is no theta. Okay, there is no theta there, and the variable is D3. Okay, so what we'll get is 1 0 0 L2 0 1 0 0, and what we'll be getting is 0 0 0 1 D3, and this is 0 0 0, and that's 1. Okay, so there'll be a 0 there. Okay, so this is what we're getting for the third matrix. Okay, so please note the third matrix, that in the third row there is no theta. Okay, so this one becomes an identity matrix. Now the last one, T 4 to 3, is the last one. Okay, so we take the fourth row, put it into this generalized matrix, and what we get is, please note that there is a 180 there. Now if it's a plus 180 or a minus 180, okay, there'll be no problem, because cos of minus is equal to plus. Okay, so cos of minus is equal to plus, so it doesn't matter which way you take a plus or a minus, because it's a cos alpha always. So if you look at this, what I'm saying is that in this equation, if you see, it is a cos alpha there and it's a cos alpha there. Okay, so whenever there is a cos 180, whether it's minus or it's plus, it doesn't matter. Okay, that's the reason why there'll be no difference. Now look at this matrix. What we'll get is cos 4. There is a theta there, so cos 4 minus sin 4. This is sin 4 cos 4. Now there'll be a minus because it is cos of 180. Okay, it's going to become minus 1. So this is equal to 0 0 0 0 minus 1, and this is 0 0 minus L2 0 0 0 1. Okay, so what I mean is cos of minus 180 and cos of 180 is the same value. So whether you put plus or minus 180 in terms of this rotation here, okay, it won't make any difference. So we have got our 4 matrices which are taking you from the 4th frame to the 1st frame. All we need to do is to multiply it out now, okay, and we can get the matrix. Now this is the reason why we need to put and understand this DH parameter very, very carefully, okay, and very carefully and very systematically, because the computer program operates like this. So all these simulation softwares, okay, for forward kinematics, inverse kinematics, they operate like this. Okay, so this is what we need to understand. Now let's look at industrial manipulator. So an industrial manipulator like the Puma robot. So the Puma robot was one of the first robots which was made about 1960s. So 1960s, one of the first robots that was made by the Unimation company was called the Puma, and this was basically made for assembly. This is called primary. So primary universal machine for assembly. So that's where the name Puma comes from. Okay. Now this, of course, the Unimation company is not there anymore. It has been bought over by Kawasaki, and this robot is also not there anymore. Okay, but 1960, this is one of the earliest robots, and a lot of research has been done on in terms of kinematics, dynamics, etc. Now this is what it looks like. Now it has 6 degrees of freedom, and the first degree of freedom is called the waist, which is this one. So let's look at the degrees of freedom first. So this is my first degree of freedom. Okay, this is my first degree of freedom. It can rotate like that. So just please imagine this. This is something very important you need to imagine. So this rotates about this joint like that. Okay, so this part can rotate. The second is this one, so it can rotate like that. Okay, that's my second degree of freedom. So this is called the shoulder, this is called the waist, this is called the elbow. This is my third degree of freedom. Okay. Now the fourth degree of freedom is called the pitch, roll, and yaw. So pitch, roll, and yaw is the fourth degree of freedom. Fourth, fifth, and sixth are the other 3 degrees of freedom which are intersecting at the wrist. So what are the 6 degrees of freedom? The first one is here. Okay. Second is here. Third is here. 4, 5, and 6 are here. Okay. So these are the 6 degrees of freedom of the Puma robot. Let's start off by assigning frames. Okay, how do we start assigning the frames? So I think better I'll just draw it here. Okay, that is for better understanding. Okay, so this is my Puma robot. Okay, and this is the other axis. Okay, so now the first axis is here. Okay, that's my first axis. Let me change the color. So the first axis is given here, is this axis. I take it here. So Z0 and Z1 is the rotation axis. The second axis is here. Okay, so this is my Z2. Okay, Z3 is here. Okay, now Z4 is this one. Z4. Z5 is that side. Z5, and Z6 is also here. Okay, now let's put the let's assign the x-axis. Now we see that Z0, Z1 are the same axis. Z2 is intersecting with Z1. So x is going to come outward. So x0, x1, and x2 are going to come like this. X3 is here. Okay, x4, x5, x6 are at the wrist. Okay, so what we are seeing is, let us go back now. Let us go back here now. So my Z1 is here. Z2 is the way it is drawn. Okay, Z3 is pointing this side. Now at the wrist, this is coming here. So this part is shown there. This part is shown there. Okay, so if you can imagine, my Z4 axis is that side. So this is my Z3 axis, which is going that side. Z4 is the roll axis, which is shown here. This is my roll axis. So the roll axis is there. The pitch axis is this one. This is the Z5 axis, which is pick. This is Z5, and Z6 is back this side. It's my Z6 axis. So the roll pitch yaw axis are at the wrist and they're intersecting. Now it's very important to understand this roll pitch yaw axis in terms of in robotics. So let us look at it this way. So this is my, let's say, my end effector, okay, and this is my roll axis, which is rotating like this. That is my pitch axis, which is rotating like this, and this is actually my yaw axis, which is rotating like that. So these are three orthogonal axes which are intersecting at a point. Okay, now this is the roll, this is pitch, and this is yaw. Okay, but if you assign it like this, there is a little problem with the DH parameter notation. So what we do is we rotate the yaw axis, bring it down, and make it and align it with the roll axis. So what you do find in the solution of this manipulator, the fourth axis is like this, Z4, Z5 is that side, and Z6 is this side again. Okay, because it's it can rotate. So what happens is whether it is this side or it is this side, it is relative. Okay, and if you put it on top, then there is a problem in assigning your DH parameters. So if you look in the textbook or anywhere, that is the reason for the Puma robot, the Z4 and Z6 seems to be along the same axis, but it is relative. Okay, so let's look at the x-axis. So these are the z-axis, Z1, Z2 is this side, Z3, Z4, Z5, and Z6 as shown here. Now x-axis is, as I drew, x1, x0, x1 and x2 are there, x3 is here, x4 is upward like this, x4 is upward, sorry, x3 is here, this is x3, x4 is that side, x5 is again, so the fifth axis is there, so the x4, x5 and x6 we take it together there at the same point. Okay, now let's look at the DH parameter notation and try to understand the DH parameters as it is moving from frame to frame. That's very, very important for this manipulator having 6 degrees of freedom. So let's look at the DH parameters. Let's make the DH parameter table here, DH table. Okay, A alpha D theta. Okay, 1, 2, 3, 4, 5, and 6. Now the first one, Z0, Z1 are the same axis. So as usual, it is 0, 0, 0, theta 1. It's very simple, right? So theta 1 is the variable here. Now what about the second one? The second one, what we see is that the Z2 is perpendicular to Z1 and it has rotated by 90 degrees about x1. So there's a minus 90 there. Okay, now the frames are, the origins are intersecting, so there is no distance between Z, so it is 0, 0, theta 2. Okay, so what we are seeing is that Z1 was in the upward direction and Z2 is on the right direction. Okay, so there is a 90 degree angle between them and it's a minus. Then from Z3 we move on to, sorry, from the second frame we move on to the third frame. Now what you can see is that there is a distance here and there is also a distance along this side. Okay, so if the origin, let me rub this off to look at the origin more clearly. Okay, now if you look at the origin more clearly, this is the origin here. It has moved like this, then it has gone forward like that, then it has come here. So there are two distances. One distance is here, okay, and another distance is here. Okay, so that is the two distances. Now those two distances are given in this figure. This is A3 and there is a D4 there. So these are the distances, sorry, this is not the second link is this one. Yeah. So now if you go back and if you just look at the distances here, what are the distances? One is your A2 is this distance. So this is a distance A2. Okay. And there is an offset distance which is D3 there. So there is a distance here, D2 and D2. So now we have our DH parameter table where we are making, sorry, A3 and D3. Okay. So what is the angle between the, what is the distance? We are saying the distance between between the okay. Now what is the distance between the z-axis? The distance between the z-axis is a2. What is the distance between what is the angle between the z's? There is no angle because they are parallel. What is the distance between the x-axis? Now there is a distance between the x-axis because one x-axis is this side, the other x-axis is this side, so there is a distance there, and this one is my d3. Okay, this is my d3 and the variable is theta 3. Now from here we go here. Now between the fourth frame and the third frame, what is the distance? There is a shift in the origins. You can see there is a shift on this side in the origins, plus there is a length there which is d4. Okay, so my z4 is in this direction. Let me rub it out, and so my z4 is in this direction. X 4, 5 and 6 are there. Okay, z4 is here, so this axis is going like this, and this z3 is here, so there is a distance here now. Okay, that is my a3, plus there is a length between the x-axis, so x3 is here and x4 is there, that is d4. Okay, so what is the distance between the z-axis? The distance between z-axis is a3. Okay, so it is a3. Now z4 and z3 are again they are not in the same direction, so z3 has rotated by 90 degrees about the x-axis and becomes z4, so it's a minus 90. Okay, and the distance between the x-axis is d4 and the variable is theta 4. Okay, now what about the fifth one? Now where is the fifth axis? The fifth z4 is that side, that is z5, sorry, z4 z5. Now what is the angle between them? It is 90 again. Now how did z4 become z5? It rotated anti-clockwise about the x-axis, so it's a plus 90. Okay, now what is the distance between the z-axis? They are intersecting, so it is 0. What is the distance between the x-axis? They are also intersecting, so it's 0, so it's theta 5. Okay, and what about the last one? Now z5 has become z6 in this direction, so it has moved like this, which is clockwise about about x, and it is minus 90 then. It is 0, 0, theta 6. Okay, so this is the DH parameter table for the Puma robot, which is an industrial robot. Now we need to look at the wrist axis again, okay, because this is a little confusing. So I'll just look at the wrist axis very quickly. Okay, just for understanding, let's do the wrist again. So this is my z4. z3 was in that direction. z4 is this direction. z5 is this direction, and z6 is back here. z6, okay, along z4 only. Where is x4? x4, x5 and x6 are there. Okay, so now if you see what is the angle, how it is between z3 and z4. z3 is rotating by clockwise, so it is minus 90 there, then becoming z4. Now z4 is becoming z5 by rotating anti-clockwise about x, so it is a plus 90 there. Okay, then z5 is again becoming z6 like this by rotating 90, but that is clockwise. Okay, so that is a minus 90 again. Okay, so this plus 90 minus 90 that we are writing here essentially is because of the clockwise and anti-clockwise rotation of the z-axis about the x-axis. Now let's now how do we proceed from here? So how we proceed is essentially we take every row, put it in the generalized matrix, and we are going to get our the combined matrix, which will take me from one frame to another frame. Then if I multiply all of them, what will happen is I will get my the generalized matrix, which will take me from the 0 frame to the base frame, right? So this is the way we do our kinematics. Sorry, not our kinematics, and we get the transformation matrix from the nth frame to the 0th frame. Okay, and when we multiply them all out, we basically get the relationship between the last frame and the 0 frame. Okay, so it is advisable that you should try this out by yourself, because you should be able to assign DH parameters by yourself correctly, then find the DH parameter table, and then from the DH parameter table you just have to take one row at a time, put it in that generalized matrix, and then proceed. Okay, so today's class we discussed about the generalized matrix, which will take you from one frame to another frame, and by using which the program actually does forward kinematics and inverse kinematics. So when you're writing a program, you have to use that matrix. Okay, and so we'll stop here today, and in the next class we'll move on to forward kinematics. That is, how do we go from the, what is the relation between the end effector to the base coordinate system. Okay, so we'll stop here for this class. Thank you.